In this lecture, we're going to learn how to use the separation of variable techniques in spherical coordinates. There's lots of problems, as you guys have seen already, in E&M that lend themselves better to spherical coordinates. So we have to be able to also solve Laplace's equation in those spherical coordinates where we're defining boundary conditions on spherical surfaces. So that's what we're going to learn about in this lecture. All right, so we'll get started. Let's say we have a round object. Okay, so we'll just go with our classic sphere here. Okay, and we can just remind ourselves about our coordinate system. That point is the origin is going to be in the center of the sphere. And I'm going to have z going up, call it y, and x. And if there was some point up here, I could define its position in spherical coordinates, where that would be defined by its r value, or its distance from the origin, by this angle here from the z-axis, theta. And then if I were to project this down in the xy plane, then I could also use a position phi to define the angle. Okay, so that's our spherical coordinate system. Okay, you might have noticed we simplified Laplace's equation down to just two terms, or a dependence on two variables in the last example. We're going to do the same thing here as well. Okay, so we need to assume, in this case, azimuthal symmetry, which basically means V can depend on R or on theta, but not on phi. Okay, so what that means basically is if I go around my sphere here, I could have a potential that could change with the distance from the origin. It can also change with this theta, which would give me, right, different kind of layers of potentially, okay? But as I go around the sphere in this phi direction, the potential can't change. So I can rotate it that way, and it has that kind of symmetry, okay? That allows us to simplify Laplace's equation because we can get rid of that third term. Oops. Let's see. Yeah. We're going to get rid of that term. So if the potential has no dependence on phi, we can assume that the derivative with respect to phi is 0. Okay, so the whole point here is to take a potential that could look like this and make it a potential that just depends on r and theta. Okay, so if I write out Laplace's equation in spherical coordinates, again, if you guys want, you could find this, I think, in the back of your book, or you can just Google it. Still a partial differential equation, so those are partial derivatives. Okay, r squared, this is going to be dv dr. And the second term looks like r squared sine theta, partial derivative with respect to theta, okay? And another sine theta in here, another partial derivative, okay, and that's all equal to 0. So it's more complicated, obviously, than Laplace's equation in Cartesian coordinates, but it's still a second order differential equation. I've got an r right here, because there's two derivatives with respect to each variable in each term. Okay, we are going to simplify it the same way we did before. We're going to simplify it, and then we're going to separate the variables. So the first thing I'm going to do here is I'm going to cancel some common terms. Just get them out. I can divide both everything in the equation by 1 over r squared and get rid of them. Okay. And that's going to simplify this a little bit. So now it'll look like that. Okay. And then the next step is I'm going to separate the variables. Okay, so let me move over to the next slide. Okay, and I'm going to separate the variables, basically doing the same thing that I did before. Okay, so we're going to separate the variables by assuming a solution. And that solution is going to, again, depend on r and theta. Okay, and it's going to look like a big R, and we'll call that a big theta that depends on theta. Okay, so these again are just general assumptions I'm making that I can write the general solution as the product of two functions, one that just depends on r and one that just depends on theta. Okay, so if I plug that into Laplace's equation, I'm going to do that one term at a time. That gives me this term. I can pull out of this first set of derivatives because that particular function does not depend on r. Okay, so that's going to leave me with that as the first term. And again, similarly, the second term I can pull out my function big R because it doesn't have any theta dependence. Okay. And that's all going to be equal to 0. Okay, hopefully you can see where we're going here. We plugged it in. Okay, and now I've got this leading term out here, and I've got this leading term on this second term. So if I divide again by my potential, then I can separate variables. So just like we did before, now I'm going to divide by what my assumed solution is. Okay, and when I do that, that's going to simplify Laplace's equation into two terms, each term just depending on one of the variables. The first term just depends on our variable r. And in fact, I always forget to do this. I can write these now as ordinary derivatives rather than partial derivatives, because everything in this particular term has no dependence on theta. Okay, and then over here, same thing. I get 1 over big theta here, 1 over the sine of theta. These are now ordinary derivatives. Boom. Okay, so I've separated the variables. Okay, cool. Notice this term only depends on r, and this term only depends on theta. Okay, but they're kind of big and they're kind of nasty. All right, let's go ahead and copy that over. Okay, just like before, I can make this argument. I can define this one as C1 and this whole second term as C2. Okay, and I know that C1 plus C2 have to equal 0. Okay, so that's just like what I did before. Okay, same as before. Okay, I know that C1 and C2 are constant, okay? They're constant, again, for the same reason as before. This term doesn't have any dependence on theta. Okay, so if I change the R value, if this wasn't constant, I could change the R value. I'd get a different value over here. But if I'm changing R, there's no way that would change this side. And so there's no way this side of the function could change to preserve the fact that summing these two terms is going to equal 0. Okay, so I know that C1 and C2 are constant. All right, so now we have to kind of give ourselves a break. This is what I call math stuff that someone else figured out. Okay, that sounds like a cop-out, but it's just true. Okay, so some of this stuff is a little bit too hard. So we're just gonna stand on the shoulder of giants and use some things that we know based on hard work that some mathematicians did a long time ago. Okay, so I know that the C2 term, okay, which is the one that has the theta dependence, okay, it cannot blow up, which means it can't get really, really big. So V going to infinity if R is finite, okay? So as long as R is some reasonable number, okay, we can't have this second term blowing up because that would make no sense, all right? Looking at this term compared to what we had before, it's a little bit hard to tell what that actually means, okay? And again, that's why we're standing on the shoulders of giants, okay? So based on what other people have done, this means, okay, that I know that that C2 term has to be less than 0. And in fact, I know that C2 has to equal negative L times L plus 1, where L is an integer and L can be greater than or equal to 0. Okay, so I can't prove this. I will not, and I am not sorry. Okay, sometimes we have to stand on the shoulders of giants. That's what we're doing. Okay, so I know that if, okay, C2 is equal to all this stuff, then that means that C1 has to be the positive version of that, okay, in order for those two to cancel out, okay? Because I know that C1 plus C2 still has to equal 0. Okay, so what does this tell me? If I look back here, that means that this term here is C1. So that means that first term has to be equal to L plus 1 times R. Okay, so all I did was I set this whole thing equal to what I knew C1 had to be equal to, and then I multiplied both sides by R. I'm dropping the little r dependence on R just to shorthand that. Okay. Again, without proving it, I'm going to tell you that the general solution is that our R function is equal to A times R to the L plus B over R to the L plus 1. Okay, that's not so obvious. Okay, that's not as easy as what we did before or as obvious, but I invite you, if you want, you can try to plug it in if you want. Okay, and we're not going to do that here because I don't want to waste your time. You guys can do it on your own. Okay, where you could use Mathematica to prove to yourself that that's true. Okay, the other one, the other term is harder. Okay, Okay, so I know that the other term implies that the derivative of sine of theta times the derivative with respect to theta of our big theta is equal to negative L plus 1 times the sine of theta. Oops. Big theta, okay? This is not so easy, okay? Again, even harder to look at. We can look at some special cases. So let's look at L equals 0, okay? If I set L equal to 0, then I get this guy. Oops, to make sure I'm making that a big guy. Okay, this implies that my big theta is equal to 1 or any other constant. Okay, which I could absorb into the overall constant by just dividing the whole equation by whatever that constant is. So basically, if I said this was 2, I could divide the whole general solution, which is going to be this guy times this guy by 2, and A and B would end up being divided by 2, okay? So we'll pick the simplest constant, which is 1, and proceed with that, okay? And let's think about what happens when L is equal to 1. Okay, now I have this relationship. Oh, by the way, I didn't really explain that. The reason why theta equal 1 works is because when I put a constant, if big theta is just equal to 1, this derivative is going to give me 0. Okay, so the whole left-hand side would be equal to 0. Okay, that's why that works. All right, let's do this next one. Okay, now I've got this relationship. Okay, this implies that big theta with respect to theta is equal to the cosine of theta. Okay, again, looking at it, not that obvious, but I invite you to plug it in and check, okay? Plug it in and check. I don't want to bother doing that now. That's pretty quick. Okay, so we're building up. We could keep going with this and write out a bunch of different terms and then stare at them and look at a general, look for some pattern to come up with a general solution. Luckily, someone else has already done that, so we don't have to go through the hard work of doing that. And if it turns out that in general, okay, the solutions for our big theta, okay, at different L values, okay, remember, because big theta, right, when I solve this, it has an L dependence here in this term here. So for different L values, the solution to big theta is going to be equal to what are called Lagrange polynomials evaluated at cosine of theta. Okay, so I'll just write out what they are now, okay, or at least a few of them, okay. If L is equal to 0, then our first Lagrange polynomial evaluated at cosine theta is equal to 1, okay. That's what we found here. Okay, that was our first solution. Okay, if L is equal to 1, then we found a different solution. Okay, in that case, it was equal to cosine of theta. That's what we found up here. L was equal to 1. That left us with this differential equation to solve. We figured out a solution is that our big theta is equal to cosine theta, and that's basically what we're saying here. Okay, so then I would plug in this guy for this. There's our solution. Okay, we didn't go any further than that, but we can go a few further. Okay, so let's do L equals 2, and the next term is gonna be a little bit more complex still. Okay. Any P sub L x, where x could be any function. In this case, x is cosine theta. X can just be x, or you can plug in another function in there. Okay. They are known as Legendre polynomials. I think I've been saying that wrong my whole life. I always call them Lagrange polynomials. Okay, Legendre polynomials. Okay, in this particular case, we are saying x is equal to the cosine of theta. Okay, but in general, they're just p evaluated at some x. Okay, and you can determine the formula for these using something known as Rodriguez's formula. Which tells you that the Elf polynomial is going to be equal to 1 over 2 to the L times L factorial times x squared minus 1, and all of that taken to the L. Okay, so thank goodness we did not have to figure that out. Okay, so let's put together what we have so far. Okay, we have a general solution for a particular L value that looks like, right, this is our general for an L value. Okay, and that's going to look like our potential for that particular L value is going to be equal to our big R, which depends just on the radius, our big theta, which just depends on theta. Okay, and then we've got some constants here. Okay, so A times R to the L plus B over R to the L plus 1 times our Lagrange polynomial evaluated at cosine of theta. Okay. I know that this general solution, it satisfies our Laplace's equation in spherical coordinates as long as I can assume that there is no phi dependence. Okay, so we found a really nice general solution for this particular problem. Okay, so similar to what we did before, I'm going to show you that any potential that we can define as depending on r and theta in a spherical coordinate system, it can be written as a sum of these v sub l's. Okay, so these v sub l's, it's kind of like the Fourier sine series. I could write any function as a combination of those sine series. Now I can write any potential as a sum of these particular terms, where I'm going to write change what the L value is, and then there's going to be a different coefficient out front. Okay, so what this says is if I want to specify a particular potential that's going to satisfy a particular set of boundary conditions, I can sum over a set of functions, okay, from L to infinity, where the coefficients are also now going to depend on L because each term is going to have its own coefficients, just like it did in the Fourier sine series. So these B and A are going to have L dependence as well because they're going to change for different terms. Okay, and this again is our Lagrange polynomial, and that is evaluated at the cosine of theta. Okay, so I just want you to note A and B can change with L, oops, not that big L, L2. Okay, so what are we going to do with this? Just like we did before, okay, we are going to use this to find the right A sub L and B sub L to build a solution that fits our boundary conditions. Okay, so I'm going to show you guys a little bit more about these Lagrange polynomials in Mathematica, and then we'll do some examples to show you how you go about this in spherical coordinates.